topic the related to the Church Turing thesis, that is part of the variants of Turing machine and linear bounded automata as a model 5 as a part of the computer automata theory and computability for 5th semester. So coming to here the discussion, we are going to be follow the presentation milestones are there. So these milestones going to be say about the concept, that is a linear bounded automata, of course we discuss, and Church Turing thesis is a motivation towards the further discussion of this Turing machine. The as a part of the linear bounded automata is important because the set of sensitive language is accepted by the model. So that is going to be discussed, that is a storage the length of the tape going to be finitized. So finitized tape is going to be transformed as an Turing machine as a linear binding automata with a tape length is linear function. So the and develop the relation between this CSL and linear bounded automata. Of course, the most of the compiler languages they are sharing the sensitive and context free languages. The linear bounded automata, of course, non-determinate text machine which a single tape length restricted to linear function. So having understood this, the concept, so you can see the concept called Church Turing thesis. Church Turing thesis is developed during 1970. Many technique to control the single quantum system have been evolved, but modest success, the average success. But an experimental prototype for performing quantum cryptography, even at the initial level, may be useful for some real world applications. So most of the real world applications may be a banking system, maybe the password cracking or the internet hacking, the website hacking, the so much revenue generative the commercial aspects which depends upon the crypting those passwords and all those. So that is performed with the help of quantum cryptography. That initial level may be useful for some real world applications. Reminding this Church Turing thesis, which declares that any algorithm can be performed on any computing machine, can be performed on Turing machine also. So there is a n number of algorithm, may be simple or complex, can be performed on any machine, performed on Turing machine also. Miniaturization of chips has enhanced the power of computer. Is Moore's law says doubling that computation power every year. So that is a miniaturization of chips also look after. The growth of computer power is now described by Moore's law, state that computer power will be double for constant cost once in every 2 years. So even in every 2 years that potentiality of the computer computation power as twice in every 2 years. Now it is feeling that limit to this doubling power will reach in 2 or 3 decades. Right? So now it is felt that by observing this the potentiality of the other computing limit to our problems, the problems arise in industry or in the human era, so that limit to this doubling power will be reached in 2 to 3 decades. Since the quantum effects will start to interfere in the functioning of electronic devices, so it participate in functioning of electronic devices as they are made smaller and smaller. So the device becomes smaller and smaller, so that comp effect will be there. Church-Turing thesis. So efforts are on to provide a theory of quantum computation, so which will be compensate for the possible failure of the Moore's law. What Moore said, so that going to be dark here, that going to be dark, that going to be tough to say like that. So this problems arise as an algorithm require polynomial time was considered an efficient algorithm. Polynomial is a solvable. These are cheaper algorithm. These are can be solvable with the minimum computations. A strengthening version of the Church-Turing thesis was enunciated. The strengthened versions of this Church-Turing thesis. Any algorithm process can simulate efficiently by Turing machine. So Turing machine is able to simulate. But challenge to strong Church-Turing thesis arose from an analog computation. So analog computation will be is a major hurdles here. So digital computation, as Moore said, it may true for digital computation. For analog computation, it may not so. There is a huge challenge are there. So the Church-Turing thesis, they proclaimed this kind of the data that is analog computation is going to be complex. Certain type of analog computers solve some problems efficiently, where these problems had no efficient solution on a Turing machine. So Turing machine not able to provide solution for this kind of problems efficiently, where analog computers perform that. But when the presence of noise was taken into account, the power of analog computer is disappeared. So that is a limitation of the analog computers. Analog computer cannot perform all the data sets as a digital computer that does. The presence of noise was taken into account. The presence of noise, the percentage of noise, so that may be a different type of noise may be there when you are collecting the input samples. So their noises are naturally introduced. Noises are part and parcel of the data, part and parcel of the inputs. There are some situations or industry situation constraints. So noise will be always there. Maximum noise will be there. Less information will be there. So the less noise and more information will be very rare case. So that may not be challenging problems. So the challenging problems is more noise and less data. Those data are very precious. So in such a case, that to analog computers will be darkened. They will unable to provide their show. They are unable to provide the solutions as the noiseless data is entered for the analog computers. So in mid 1970, Robert Sauvé et al. Given a randomized algorithm for testing the primality of the number. So prime number testing. So the generates the prime number and test them, so that large prime number it may be is required most of the encrypting algorithms. So their prime number they will use as a for primary key and secondary secret keys, right? So that primality testing algorithms is a most complex algorithm. So that NP problems. So that random is algorithm for testing those prime number testing algorithm. So deterministic polynomial algorithm was given by Manindra Agarwal et al. From IIT Kanpur in 2003. This pioneer to modification of the Church thesis. This went to the extent of the polish the Church thesis. Polish the Church thesis. So that is the effort of this Manindra Agarwal and effort team. So Church thesis, there is an effective procedure for solving a problem if and only if there is a Turing machine that halts for all inputs and solve the problems. So those Turing machines which halts accurately for all inputs, such are called effective. Such procedure called Church Turing thesis, right? So the Turing machine stops, halts for certain inputs, either reject or accept, no problem, but it halts to it took a decision to halt, so it saved the computational aspects. Instead of halting, it postponed to halt or dilemma to halt, inconsistent to halt, or it may be stuck in the loop. So that is a computational burden. So that is not a situation. So situation or procedure going to be exhibits its potentiality to provide a solution, halt for all inputs. Such procedure solves the problem. Such is a Turing Church Turing thesis. Many other computing models are exist in the literature, but equivalent to or subsumed by Turing machines. There is no more powerful machines strictly cannot be proved. DFA, that is deterministic finite automata, and pushdown automata do not model all effective procedures and computable functions, but only subset. They are not effective. All effective procedures are computable functions, but still they are all the subset. So they are not the major sets, major landmarks, or they are not the pioneers. If something can be computed, it can be computed by Turing machine. So it can be computed by the Turing machine. So note that this is called thesis. Something can be computed, it can be computed by Turing machine. This is called a thesis, not a theorem. This is thesis, not a theorem. It cannot be proved because the term can be computed is too vague. So term computed is too vague, so it cannot be termed, but it is universally accepted as a true statement across the globe, is considered as a true statement. So the strong thesis of Church, an algorithmic process can be simulated efficiently using a non-deterministic Turing machine. So this procedure can be bring out from this non-deterministic Turing machine. During 85, David Dutch tried to build a computing devices using a quantum mechanics. So during 85 is tried. Computers are physical objects and computations are physical processes. So what computer cannot do, computer determine the physics alone, not by pure mathematicians, that David Dutch said. But it cannot be known whether Dutch's notion of universal computing, quantum computers, will efficiently simulate any physical process. So that is not known. So 94, Peter Shor proved that finding the prime number factors composing numbers, the discrete logarithm problems. So finding the positive value of such, that is b is equal to a power s for given positive integers a and b could be solved efficiently by quantum computers. So a and positive integers could be solved by using quantum computers, that is a positive value of the s. So this may pointer to prove that quantum computers are more efficient than Turing machine and classical computers. So that is more efficient than Turing machine. So given that Church Turing thesis, what does this about computability? Are there things even Turing machine cannot do? If there are, then there is things that simply cannot be computed. Cannot be computed. So not with a Turing machine, not with a laptop, so not with a supercomputer. So there are things that Turing machine cannot do. Things still Turing machine is unable to do. The Church-Turing thesis declare, in other words, there is no problem for which can be described algorithm that cannot be done by Turing machine, which can describe by algorithm that cannot be done by the Turing machine. So that is the Church thesis strong theory, which is narrated about the problem for certain inputs Turing machine perform. That is a part of the solution, is a Church-Turing thesis. Continuation of that, there is a notations represent two components of the instruction with a component 0 is equal to 1, 1 is equal to 1 1, 2 is equal to 3 1, 3 is equal to 4 1. So this is the instructions. So n is equal to 1 1 1, that is a n plus 1 ones. So n plus 1 ones from this data. We encode qn as a n plus 1 ones. We encode symbol an, that is a n plus 1 ones. So we encode move left as a 1 and move right to as a 1 1. So 1 1 0 1 1 0 5 ones 0 3 ones 0 1 0 0 1 0 1 1 0 1, so on. That is. So q3 q a2 q4 a2 left, q0 a1 q1 a1 right. So any Turing machine can encode as a unique long string of 0 and 1s, begin with 1. So begin with 1, we can perform that is. So that is, let Tn be the Turing machine, T of n be the Turing machine whose encoding is the number of n. So problems, set of all languages whose complement are in non-polynomial is called a co-non-polynomial. Prove that NP is equal to co-non-polynomial if and if there is some NP complete problems whose complement is in NP. Whose complement in NP. So only if take an NP complete problem L, then complement the L is in co NP is equal to NP. So co is a complement NP is equal to NP. So let let P be the that is a NP. So this is NP complete. So this is NP complete, and P complement belongs to NP. So let L be the language in NP. We get a polynomial reduction pi that is of L to P, and hence the polynomial reduction psi of L complement to P complement. So we prove NP, the complement NP combined psi and non-deterministic polynomial time algorithms for P to get a non-deterministic. So that can be observed in this problem. So that is a NP is equal to complement of NP. Yes, seen that. So example 2, the string W. So W is in 0, 1. That is a flower bracket 0, 1 flower bracket whole star. So that is a W. From the input bank we can get a W. W ends with a 0. So that is 0 0 0 1 0 0 1 0 1 1 0. So string ends with a 0. So not epsilon, not empty. So Q is equal to Q0 comma Q1 comma Q2. So that tape symbol, input symbols 0 comma 1 comma B of Turing machine, sigma that is input 0 comma 1, and F is a final state Q2. So B is a blank for the tape, that is a Turing machine tape. So Q0 is a scan write state, Q1 is the verify 0 state. So let's see that inputs 0, 1 and blank. So we can have, so when Q0 is the initial state and 0 is input, then it remain in the same state, and 0 will be retained, and read write head move towards the right side, right? So when 1, the same situation, 1 will be written, head will be moved, keep moving right side. When blank, it will be change the state, and blank will be there and turn towards the left side. Direction will be reverse change, that is. So Q1, that is changes to Q2, and 0 will be retained, move towards the right side. 1 in case no response, blank in no response when you are Q1. Q2, any input 0, 1, B, no response. So that is ends, right? So overall approach will show that the language LD is not recursive enumerable. From this is it will be follow that is not a recursive. So using this here will show that the language LU is not a recursive. From this it will follow that halting problem is undecidable. So universal language Turing machine simulates the arbitrary Turing machine on arbitrary inputs. So universal Turing machine essentially achieves this by reading both the description of the machine to be simulated. So description of the machine going to be simulated, as well as the input to that machine from its own tape. LU is a recursively enumerable but not recursive. Enumerable but not recursive. LU is a set of binary strings, that is a universal language, consists of encoded pairs M, W, such that M is a machine encoding the Turing machine and W is the encoding of the binary input strings accepted by the Turing machine. So undecidable language for which membership cannot be decided by an algorithm equivalently cannot be recognized by the Turing machine that halts for all inputs. So that is the equivalently. So example glinks nist.gov tats or HTML. So such universal language are undecidable. The language define the language LU as follows. LU is a X, flower bracket open X, where X is an 0, 1 whole star and X is less than M, W the string, where M is a Turing machine and W is a strings belongs to AL of M. Let X be the 0, 1 whole star, then either X does not have Turing machine prefix, in which X is not in LU. So X has a Turing machine prefix, that is X less than or less than M, W, less than M, W either. So A case, W is not in L of M, in which case X is not in LU. If it is not in LM, it is also not in LU. So W is in LM, in which case X is in LU. So P3 primitive programming language. P is a Kuroda Bohm 1964. First go to less imperative language proved by Turing complete. So universal. So one of its better known 3 variants has 3 instruction in total. Another variant called P3 also universal and having just 7 instruction, or less than, greater than, plus, minus, square open bracket, square end bracket, and small o. So P operates on input memory input or memory tape of cell by moving a pointer left to left, similar to the Turing machine. P3 program takes binary inputs and generates the binary outputs. Also, special symbol dot. P3 by left shift, example input 0010, output 00101. So greater than bracket, that is what is the dot, that dot, greater than close square bracket, less than open square bracket, less than close, and greater than, that is dot. Tape alphabet has three symbols, that is 0, 1, dot. Tape is padded with the dot on the cells before and after the binary input. So that is padded, that is. So the crucial dot is a crucial for loops and halting of the programs. An output tape or to which the symbol is in the pointer cell can be written in a write only sequential manner. So, and if a dot is output program halts. So dot is a very important notation here. So compare this P3 and universal. The input Turing machine M with the input alphabets sigma. Final state and string W is in sigma star. Notes that universal language is P3 expressed as a language. Asking if universal language is a recursive, if the same as querying if P3 is a decidable. So LU is a recursible, same as querying if P3 is a decidable. It will show LV is not a recursive. From this it will follow that P3 is an undecidable. P3 is a undecidable. From this point further show that halting problem is a undecidable. So halting problem is a undecidable. So note that LU is a recursive if M is a DFA. LU is a recursible if M is a DFA. So from this, all this concept, Church Turing machine, universal language, P3, and all these concepts we collected from the textbooks Elan-Rich Automata Compatibility and Complexity. It's in Pearson Education 12 and 13. Of course, most of the material from Misra and Chandrasekhan, especially this model 3 and model 4. Model 4 and model 5 of this automata theory and computability from this book. And also additional information we extracted the Woodcroft, Motwani, Ullman, Introduction to Computer Theory, Languages and Computation, Pearson Education publication. Add-on, that is a material from Michael Schipser, Introduction to the Theory of Computation, 3rd edition, Cengage Learning. Martin, that is a Introduction to Language and Theory of Computations, 3rd edition, Tata McGrail Publishing Company Limited, 2013. Apart from this, there is also materials from magazines or some scientific journals, and also internet are huge resource of providing the material for the interesting topic related to this Church Turing thesis, related to the part of the variant of Turing machine and linear bounded data automata as a part of the automata theory and computability. With this, thank you for patient listening. The topic linear bounded automata and Church Turing thesis along with the universal language and P3 and universal languages. So thanks to coordinator and moderator, subjects expert. Thank you once again. Thank you one and all.